Okay, so welcome to the lecture 3. Before I continue from the previous lecture, because we stopped in the middle of lecture 2, so I'm going to just have a quick review, 5 minutes review on what I've delivered last session. Last session we talked about noise. And then for this noise, we derived few mathematical model into two categories, for the time domain and frequency domain. So if I just want to show you the most important equations, we said that noise is a random process. It means that we do not know the instantaneous value of noise. And a random process, then we define the average power. In the time domain, we define the average power equals to limit period to infinity, 1 over period integral over period of Vn squared. And we said that this is not zero. Okay? And then we define the Vrms and said that this RMS, the relation between the average power and the RMS is this. And then we said that if we have multiple sources of voltage noise, then we can add them together by this formula, that the Vn RMS of total equals to square root of Vn 1 squared plus Vn 2 squared, and so on. So this is for the time domain definition. And then for the frequency domain definition, we defined a term as a power spectral density, PSD. So just remove this, what will happen? And then in the PSD, we say that if you have a time domain signal xt, and then it goes into a system with the transfer function hf, and then we have yt, so the PSD of xt equals to Sx of f, and then the PSD of yt is S yf, and then the relation between these two is hf squared. I mean Sy equals to Sx multiplied by absolute of hf squared. Okay? The same definition we have in the frequency domain for the average power, and we said that average power is integral again 0 to infinity S XF TF. And this value and this value are similar. And this is for a signal which has a unlimited bandwidth. For a limited bandwidth, then we have to replace the integral by, again, P of, for example, total equals to integral of FL to FH SXF. Another thing that I mentioned is that for any system, so we have a bandwidth and we have an effective bandwidth, and these two could be different because the transfer function is the transfer function of the power. So the bandwidth is the bandwidth of the voltage, and then we have to find the bandwidth of the power, which we call it effective bandwidth. I will solve one question for you, and then you will see that what does it mean. Actually, we have one example in the class, but in one problem we will see it more accurate. And then we have the and then we have different type of noise in the electronic circuit. So I defined the types of noise. Or sources of noise. And then we had the thermal noise, which we saw it is mainly coming from the resistors. And then we had shot noise, which comes at the p-n junctions. So it happens when we have a p-n junction, and then we had a flicker noise. Which originates from the impurities in the semiconductors. So the first one, so the first one is actually mainly happens in the resistors. The second one, we have it in the BJTs. And the third one is coming in the MOSFETs. The first two are white noise, and the third one is dependent on the frequency. And the dependency is 1 over F. Okay? White noise. The first two, both of them. I mean the thermal noise and shot noise, both of them are white noise. And the flicker noise, we call it pink. So it's pink noise. It's dependent on the frequency. And I'm not going to mention again the formulas because they are already in the lecture notes. It takes time. The next one is when we have a noisy network. assume that we have a noisy network. So this is a noisy network. Assume it's a two-port network, input, output. Then we can model this with a noiseless network in conjunction with two sources of noise which we call them as the input referred noise sources. I mean that any element inside this network which creates noise, including the transistors and resistors, then we move that source of noise into the input of this two-port network, and then we have a noise-free or noiseless network in conjunction with the sources of noise.
Is it that the Vn and the In of that noiseless network represents the noise in that noisy network?
Yes, they all. So inside this noisy network, we have multiple sources of voltage and current source of noise. Okay? And then all of them together, then we can model all these into two sources of noise. Okay? This is what we have done for the resistors.
One other question. Vn and In are supposedly constant, so if we model it in that way, the noise is constant.
The noise is, what do you mean constant?
The sources, Vn and In.
The source could be constant, could be frequency dependent, and actually the source is dependent on the values that you have in the network. For example, a resistor, the noise of a resistor depends on the value of the nominal value of the resistor, the temperature, and the bandwidth. So these three could change.
They may vary.
Definitely, they are not constant. If we know the parameters of a network, then we can say, yeah, this is constant. Yeah. Or, for example, for the shot noise, it is mainly dependent on the biasing of the transistor. When we bias the transistor, then we can say that, okay, the source noise is this value. And then I defined one parameter as noise figure or noise factor, and we said that the noise factor is how much noise, a noise factor of a system or a network is how much noise that it adds to the input signal. It means that it is SNR, signal to noise ratio at the input, divided by SNR at the output. And this is always greater than 1. I mean, we are always adding noise to a signal that we receive. Okay? So noise factor is usually we mention in the linear format, and in the dB format we call it noise figure. And noise figure is log 10 of the noise factor. We usually call noise factor as F. In the lecture note, I've written that as F.
The noise figure is in dB.
Yes. Noise figure. Usually in the data sheets, you receive a graph of the noise figure, for example, amplifier or mixer, which is dependent on the frequency, and the value is in dB. I mean, it says that, for example, this amplifier shows a noise figure of 2.2 at 2 gigahertz and then 2.4 at 4 gigahertz and so on, or a table. We modeled all the sources of noise for the BJT and also we calculated, we showed that how we can calculate the noise figure of a BJT. We will see in one of the examples, and for the MOS as well. I think I'm not going to go through these. The next thing was the amplifier, and then as amplifier is a combination of lots of transistors and components, so they usually give you two values for the two values of the Vn and In of the amplifier, the op amp. And then they said that, okay, the input referred noise of Vn is this value, nanovolt over a square root of hertz, and In, for example, picoampere over a square root of hertz, and then you need to calculate the noise figure of the system that you biased. The first example will go for this. Okay. One thing that I mentioned the other day, that in the op amp, or it's better if I go to the lecture, the corresponding lecture slide might be better. Yeah. So in the op amp, I showed you that we can calculate the Vn RMS of op amp based on the values that we get on the op amp, the FC of the corner and the white noise that which is given based on these formulas. And then I said that the Vn peak to peak is 6.6 times of the Vn RMS. So why we put this as 6.6? If you look at the distribution function of a noise, okay, we say that it's a white noise, and distribution function of a white noise is Gaussian, which is like this, okay, and then we say that the signal with the distribution function of Gaussian is like this. For example, this is the noise. This is the signal that you see. Okay, I mean the value, the amplitude of the noise is always sigma. This is the RMS value for a random process. So the RMS value of a random process, a Gaussian process, is always sigma. And then we said, okay, this is the RMS value, but what is the peak value of this signal? This is random. It's not a sine use. It's a random. I mean, what does it mean? It's random. It means that it can achieve any value. But, for example, the RMS value of this is in this region. It's from this point to this point. If it wants to, for example, achieve a value at here, then the probability is less. If it wants to achieve a value at this point, the probability is less. So what's the maximum value for this signal? Sorry? So the maximum value for this one is infinite. I mean, it can peak something here, but the probability is very, very low. Okay? So this is a random process. It means that we do not exactly what is the value. We have an idea that, okay, it follows this kind of distribution, and mainly it happens in this region, but it can also achieve something infinite. Okay? But we define fidelities. And then in the fidelity, we say that, okay, this signal, for example, up to 2 sigma has one probability. Up to 3 sigma has one probability, and so on. And then if you calculate these values, for example, 3 sigma, I believe is, when we say 3 sigma, then we go up to 99, I think. 99. Yeah. Yeah. So 99% of time, our signal is in this region. Okay? And then we say that 3.3 sigma is 99.9%. It means that only 0.1% of the time our signal is higher than this value. And then we say that, okay, this is the B peak. This is how they calculate this. And then 3.3 times multiplied by 2 is 6.6 times of the RMS. Okay? If we say that the RMS is sigma, then 3.3 times multiplied by 2 is 6.6 times of the peak. So for the random process, this is how we can say that, okay, I'm interested in only 99%, then it's 6 times. Then we say that the peak to peak is 6 times. Okay? Clear? All right. And the last part was the noise figure of a cascaded networks. So if we have multiple networks cascaded together, we said that the noise figure of the whole is actually the noise figure of the first one plus, or noise factor of the first one plus noise factor of the second one divided by the gain of the first, and noise factor of the third divided by gain of the previous stages, and so on. And we said that if the gain of the first stage is high, we can say that this part is not that much important. If we put a high gain component in the first stage of our receiver, then the noise figure of the whole system is usually the noise figure of the first stage. So usually we see that most of the receivers, they put one LNA at the beginning to reduce the effect of the noise figure of the mixers, which is usually high, and the rest of the circuit. Okay. Any question? If not, then we can continue for the new contents. All right. So up to here we understood that what's the noise. But what's the effect of the noise? I mean that, okay, we can calculate the noise figure of the system, but then from that we define another parameter which is important, especially in the receivers, is the sensitivity of the receiver. The sensitivity is defined as the minimum signal level that a receiver can detect. I mean, I say that my receiver, the sensitivity of my receiver is minus 71 dBm. It means if the signal that I receive at the port of my antenna is less than minus 71 dBm, then I cannot detect. And sensitivity is a value of bit error rate. I mean, we say that this SNR value that I need for this bit error rate is the SNR, the required SNR is 25 dB or 20 dB, and then based on that I calculate the sensitivity of my receiver. Then the sensitivity of my receiver for the corresponding bit error rate is what we calculate. Okay? So the sufficient signal to noise ratio, I mean, this is what I said, the required signal to noise ratio for the corresponding bit error rate. When you look at the bit error rate based on SNR, so I mean that if you look at this. We say that this is SNR, this is bit error rate. And then you see that so when the bit error rate is higher, the signal to noise ratio is also higher. So it's like this. No, sorry, bit error rate is lower, SNR is higher. So it's like, it's like this. It depends on the modulation. So the modulation that you have in it depends, it's FM modulation, AM modulation, QPSK. So it means that if my signal to noise, if I want to achieve a bit error rate of, for example, 10 to the power minus 3, it means that from out of 1,000 symbols that I receive, only one of them is wrong. And 999 of that is correct. Then we say that, okay, the signal to noise ratio that I need at the signal processing part, for example, is 15 dBm or 15 dB. Okay, it's in dB. SNR in dB. But if I need, for example, a bit error rate of, I don't know, 10 to the power minus 5, then the SNR should be, for example, 25. I need to increase the value for my the power of my signal to have a better receiver. Okay? So here we define the PSI, the input signal power that we received at the antenna port. The PNI is the noise power of our source or noise power of our antenna. So how an antenna can be a noisy? Why we say antenna has a noise?
Because of its configuration, it has many electrical components.
Antenna is a passive device. Antenna could be a single, for example, wire. Okay, antenna, we can model antenna with its resistance.
So thermal noise is there.
So it has a resistor, it has a thermal noise. Okay. In the components that we define, the transistors and resistors are the sources of noise. The capacitors and inductors are noise-free. I mean, ideally they are noise-free. In the high frequency, for example, in lecture 1 we showed that we can model an inductor and then inside that it has resistors. Definitely it has. But ideally, if we say that we have an ideal inductor or ideal capacitor, it means that it's noise-free. Okay? But the antenna itself can be modeled by a single resistor, and we call it RA, R of antenna. And then this is the PNI that I said, if we have antenna. But if we have source, I mean, if I connect directly a source to my receiver, then the internal resistance of that source is the PNI, is the source of the PNI. Okay? Then we define the noise figure of our system or noise factor of our system as the SNR in, which is PSI divided by PNI, and the SNR out, which is the SNR that we need. I mean, I said we find from this graph that I need a 25 dB SNR. So I know this value I know this value, I can calculate what's the noise factor of my receiver. I know this value, and then I can find this value. And this is the sensitivity. I mean, the minimum signal that we need to achieve this SNR out. Okay? Is it clear?
So PSI is basically the sensitivity.
Yes. The PSI minimum is the sensitivity. The minimum power that I can tolerate if I want to achieve this bit error rate. And it comes from here. So I know the noise factor, I know the SNR that I need from the graph, I know the input resistance of my antenna or my source, and I know the bandwidth of my system, and then I can calculate this. Okay. So one question for, okay. So, and then if we move this to dB format, so this is the linear format, but usually we are talking about the sensitivity in dB. I said my receiver sensitivity is 71 minus 71 dBm. Okay? If we want to go to dB format, then you have to get a log 10 from both sides of this. And then log 10 of this is PSN in dBm, and then these values. So log 10 of our SNR out is SNR out in dB. Log 10 of the F is the noise figure. So the log 10 of the F is the noise figure. The log 10 of the SNR out is SNR out is in dB. The log 10 of the input power is the PSN. And then, okay, the log 10 of these two. Okay, and the log 10 of B is this value. Okay, and then the log 10 is minus 174. Why? So I said that if our source or our antenna is matched to our load, then the input resistance noise is KT, okay? And then for 1 hertz, this KT is minus 174. My question is that why it's KT?
Because it gives the thermal noise.
Okay, and thermal noise is KT, or is 4 KT? So thermal noise is the square root of 4 KT. All right, I have a source. I solve it for source, and it's exactly similar for antenna, okay? So I have a source, and this source is Vs. And it has internal resistance of Rs, and it comes, I mean, this is my source. From here is this is source. And then it connects to my load. All right. We say that we have a maximum power transfer from our source to our load when Rs equal to R. Fully matched Rs equal to RL. Okay. Okay, what's the noise of my source? The noise of my source comes from this resistor. And then the noise that we have, I mean Vn equals to square root 4KT B. And assume that B equals to 1 hertz. Okay. So I can model this resistor with a noiseless resistor in series with a source of Vn. I mean, I can write down this like this. We have a Vn. So here is R, here is R, and Rs equals to RL equals to R. Okay. So what's the voltage at this point? The voltage coming from Vn only. I don't care that what's the value for Vs. We can omit this because it does not generate noise. I want to see that how much noise I received from this resistor. I mean how much noise that this resistor generates and I receive it at RL or R. Okay. So what's the voltage at this point? V out. I call this V out. So V out equals to RL divided by RL plus RS Vn. Correct? So what's the power that we have at this point? So P equals to V out squared divided by RL. Okay? So V out squared is RL squared divided by RL plus R. Squared Vn squared 1 over RL. Okay. And what was Vn? Vn was 4 kT, square root of 4 kT. All right? So the power that we have, if RL equal to RS, so the power that we have, power equals to RL. I think I made a mistake here. It has R as well because the noise coming from a resistor is dependent on the resistor value as well. Okay? So is R divided by 4R squared 4 kT R 1 over R.
Why do we have KTR, 4 KTR?
4 kTRB. So this is the noise coming from a resistor. Okay? So this is the noise which coming from if I want to model the noise of a resistor, this is the value for Vn. Clear? And then we define the dynamic range. So the dynamic range actually is equal to the maximum power that we can tolerate minus the minimum power that we can tolerate. So the minimum, we already saw that the minimum is the sensitivity of the receiver. And the maximum we will see at the end, that what's the maximum power that we can achieve we can tolerate in a receiver. Any question on the sensitivity? Okay. If not, we are going to the second section, which is linearity. But before I'm going to linearity, I just follow few definitions that you had in the signals and systems, old signals and systems. So we call a system linear. Okay. So I want to talk about linearity, so I'm defining the properties that we have. We call a system linear if the output expressed as a linear superposition of the inputs, individual inputs. I mean that if we have two inputs, x1 and x2 at the system, at the input of one linear system, then this is y2, I think. Then the output, we can say, is y1 and y2. Then if we multiply the inputs by two arbitrary values of a and b, and we have a x1 plus b x2, then the output is a1 plus a y1 plus b y2. Okay, this is the definition of a linear system. Based on this definition, we can say that if a system is y equals to x plus 1, is it linear or non-linear? Why?
Input x plus 1 and output y.
The input is x, the output is x plus 1.
Input x plus 1. Output y.
Yt equals to x t plus 1. Non-linear. Yeah.
If you multiply a scale.
If you multiply the input by k, the output doesn't multiply by k. So if a system has an offset, it's not linear. This is what I want to say. System with a DC offset, system with a non-zero initials is non-linear, always. So this is what you should know. Another thing that you should not make a mistake with linear systems is time variant systems. So time invariant systems means that if we have a time shift into the input, if we make a time shift in the input, then the same time shift happens into the output. I mean, if I have this, then this condition should be correct for an arbitrary tau. Okay, so this is time invariant. So time invariant and linear are different. So this is very important. The system could be linear, but could be time variant. Okay? But it generates a component, a frequency component, which is not in the input. I mean that if I have xt equals to a cosine omega t, and then I send it to a system of linear but time invariant. In the output, I can receive yt, which is b cosine omega t plus c cosine. Okay, I call it omega 1, I call it omega 1, I call it omega 2. I mean, a time invariant system can generate other frequencies independent of the system is linear or nonlinear. Think about it and see. Maybe you can find why. I don't want to make an example because it takes time, but you should think about it, okay? Another definition is the memoryless. So we say that a system is memoryless if the output of the system is not dependent on the previous values of the input or the output. I mean, the output of the system is exactly dependent on the current input value. Doesn't matter that previously what did happen. Okay? We say that this system does not have memory and it's memoryless or static. Does not depend on the past values. Okay? Again, this one is important. We say that if a system is memoryless and linear, then the output is definitely like this. And this alpha could be time variant. I mean, could be any function. I believe all these definitions you saw in the signal processing, I just wanted to go into the electronic behavior of this. All right? We have a memoryless but nonlinear system. Then we can say that the output could be approximated by polynomial, okay, of the input. I mean, if the input is xt, and then the output is yt, which could have a DC offset, which would have the fundamental component and all the harmony and the other derivations. Okay? And this alpha I, again, could be a time variant parameter. All right? We say that the system has an odd symmetry. Okay? This system, I mean this system that I define here, has an odd symmetry if alpha j equal to 0, if j is even. Or if the response to xt and, I mean, minus xt and xt are equal. We are very interested in these kind of systems because it does not generate DC. We call these kind of systems in electronic as a balanced system. Maybe you heard that we have a balanced mixer. Most of the differential systems has this property that they are not generating the second harmonic and not generating the DC component. And this is fantastic. Okay? And finally, we call a system as dynamic if it is not memoryless. I mean, it has a memory. The output depends on the values of the previous values of input and output. And then you know that we define the output as a convolution function of the input with the impulse response of the system. Okay? questions? This is just a review for what you knew before. And then I want to define a nonlinearity in the electronic systems. Okay, if there is no question, then we are going to the three types of nonlinearities that we have in the electronic systems. The first one is the harmonic distortion. The second one is the gain compression. And the third one is the intermodulation. So I'm going to talk about these three, and then I tell you that which one is harmful, which one we can manage somehow. And actually, when we are going to compare two systems, these are the parameters that we are going to compare. I mean, I say that, okay, my system, my receiver, the third intercept point or the third intermodulation point is this value, and for example, his design is this value. So if the third intercept point is higher, then maybe it's better.
Is this slides included recently?
Sorry?
These slides?
Yes. Yes. I think I changed this from the previous, because the previous slide, I think, following them is not that much easy. For at least for I myself, it was not that easy. So I tried to prepare new slides for you that you can follow the instructions. Anyway, if you don't have the slides, you can have this, because I don't need them. It's fine. Okay, we say that in RF electronics, a memoryless system can be approximated by this value. So if you remember from previous slide, we had another terms like this. And we say that in the electronics, only these three are important for us. Okay? The other harmonics is not that much important. I will tell you that why. Because the components which are coming from this guy and the components which are coming from this guy are the most problematic components which could be inside the region that we are, which is our interest. The components which is coming from, for example, X4 is somewhere else. I don't care. Okay? So I said that the effect of the storage elements and the higher order nonlinear terms must be carefully examined to ensure that the above equation is plausible. I mean that, okay, maybe some systems you need to take care of the influence of the other components or the memory of the system. But for now, we assume that our system is memoryless and it is approximated by this equation. Okay, if we have an input signal as this, a single tone sinus at frequency of f, that omega equals to 2 pi f, okay? And then we send it into this system with this nonlinearity. We can see that we have the first term, the second term, and the third term. All right? And if we expand cosine squared into 1 plus cosine 2 divided by 2, and expand cosine to the power 3 to the cosine of omega t and cosine of 3 omega t divided by 4, then we reaches this equation. And we see that this system generates a DC component which is coming from the second harmonic. So second harmonic gives you a DC current. Just follow me. Don't miss this part. Second harmonic generates DC components. I told you that if our system is balanced or has an odd symmetry, then we don't have DC component. I mean that if this guy is 0, then we don't have DC. Okay? And it has a fundamental frequency, which is our interest. But this fundamental frequency comes from the alpha 1, which is the gain of the system, and comes from another component which comes from this nonlinearity. Okay? So it can change the gain of my system. My interest gain is alpha 1. If we have a linear system, then yt equals to alpha 1 xt, which is alpha 1 a cosine omega t. Okay? So this alpha 1 is the gain of my system, the desired gain. But unfortunately, my gain also changed. And then we have a second harmonic and third harmonic. Okay? So I send a single tone into a nonlinear system, and I got a DC, a fundamental frequency, which is my interest, and then the second harmonic and third harmonic. If you look at the graph here, so I have the input which has a frequency only at f1, okay? And then it goes to this nonlinear system, and this nonlinear system is defined by this equation, okay? Then you see that we have a DC component. If you look at the output of my system on a spectrum analyzer, I have DC, the fundamental frequency, and the other harmonics. This is good. Somehow good. These are not. One important thing that you should see from these graphs, that the second harmonic and the third harmonic, the value that we have on the graph, is increasing by a squared and a to the power 3. I can say that the nth harmonic is increasing by an, and it is very bad. I mean that if we increase the amplitude of our input, our harmonics grows faster than our signal. Our signal increase by a, but the harmonics increase by a squared and a to the power 3. So if I increase the power at the input, then maybe the filter that I put at the output to remove the harmonics is not good enough. This is the problem that you can see. We usually put a kind of filter like this here to remove out these two harmonic. The only way that we can get rid of the harmonics is to put a filter. Okay? But if we increase the input, and the filter is not as ideal as this, filter is like this, for example. Okay? So my first signal, fundamental signal, is here, good. And then the second signal, the second harmonic, and then the third harmonic, okay? So if I increase the signal, then the harmonics increases in a rapid pace, more rapid pace. Make sense? But harmonics are good nonlinearities because you can put a filter and get rid of them easy. The next problem that we have is the gain compression. Okay? So in the gain compression, we are studying this component that I said. I assume that the gain of my transistor should increases by alpha 1. But I see that when I increase the A, when I increase my input value, then I see that the gain of my transistor is not following linearly. It changes. This is what you see in the gain compression. So I assume that when I increase the input, my output increases linearly with the slope of alpha 1 in dB. For example, if this is the dB format. Okay? But we see that, okay, the gain is not following a linear trend. It has this. And then we define a 1 dB compression point. What does it mean? It means that I expect a value of, for example, if my V out equals to 2 V in, okay? I mean, I have a gain of 2. So at this point that the V in is 10, then I assume that my V out be 20. But unfortunately, I see 19. So this is the 1 dB gain compression. It means that the output gain is 1 dB less than what I expect. Okay? And it causes by this.
Is it always 1 dB?
This is a definition. See, we define a 1 dB we define a 1 dB compression point, and then we say that the 1 dB compression point of this transistor is this value. P1 dB of this transistor is 10 dBm. I mean that if you put the input of 10 dBm, then the expected gain that you should receive is 1 dB less. Less than what, I mean the gain that you receive is 1 dB less than what you expect. Okay? It's a definition. From one transistor to another transistor is different. It is dependent on the power supply. It is dependent on the topology of the transistor. It could be a value, I can say, between minus 30 dBm to minus 15 dBm for usual amplifiers that you see in the commercial shelf.
Is this compression because of the higher order of
Yeah.
components?
Yes. So the value for alpha 3 is very low, okay? But as this term increases by increasing the amplitude of the input signal, then in higher amplitudes of the input signal, it shows its influence, okay? And this is important. This is very important, that alpha 1 and alpha 3 are not with the same sign. I mean, it does not add your gain. It always reduces your gain. Why? Again, I leave it to you. You can write down the equation for a single mass or for a single BJT and see that what's the value for alpha 1 and what's the value for alpha 3. One of them is positive, one of them is negative. Also for differential amplifiers, it's like that. And based on the alpha 1 and alpha 3, we can calculate the input 1 dB compression point. In the data sheets, they usually show this graph. I mean, in the data sheet of an amplifier or a mixer, you see this graph, that the P out divided by P in, and then they say that, okay, 1 dB compression point is this value. They can say that it is this value in the output as well. Mainly, they say the V in 1 dB point. But sometimes you can see in the data sheet that it is V out 1 dB. No difference. You can find from each other on the graph. Okay? I mentioned here. Okay, the 1 dB compression point in some modulations is important. I mean, it degrades the performance of your receiver. In some modulations, it depends on how you encode the data on the carrier. For example, in the FM modulation, it does not important. Why? Because in the FM modulation, for example, if we have a signal like this, then the output of the FM is like this. I mean, it's on the frequency of the signal. But in AM modulation, it's not. Because in AM modulation, if I send an AM modulation signal into a amplifier, and the gain, for example, at the value of A is alpha 1, and at the value of B is alpha 2, then it means that the different amplitudes amplifies with different values. The problem is this. I mean, if your input value is in this value, then it receives a gain of alpha 1. If it is in this value, again, it receives a gain of alpha 1. But if it is in this value, it receives a gain of alpha 1 minus 1 dB. This is the problem. And then your data is distorted. So AM modulation, the data encoded in the amplitude of the signal. And and different amplitudes amplifies with different values. This is the problem. Clear or not? Good. Question. The next one is the intermodulation. So far what we discussed is about if we have only one single tone signal into our system. Okay? Now if our signal has two tones, I mean that we have two sinus at omega 1 and omega 2 is going into a nonlinear system that I defined previously, approximated by a third order polynomial. Okay? Then we can write down that our output is again alpha 1, the fundamental, alpha 2, this is squared, and alpha 3, again the input to the power 3. This is what we have from the transfer function of our system. Okay? So this, if you expand this expression and then just put away the DC term, which is already there, and the harmonics, which I said that we can get rid of them by filters, and we have another two terms. The first one is the one that we are interested, which is at omega 1 plus omega 2, or omega 1 minus omega 2, because when we have two inputs, for example, in the mixer, we say that we have two inputs in the mixer, omega 1, omega 2, and then this is a multiplier or mixer. So the output is cosine omega 1 cosine omega 2. Okay? So what you received from this is cosine omega 1 plus omega 2 and cosine omega 1 minus omega 2. So these are the two components that I want. I like them. So what we have in the output, the components at omega 1 plus omega 2, omega 1 minus omega 2, which are our interest. We have DC component. We have some harmonics of our signal, I mean 2 omega 1, 2 omega 2, 3 omega 1, and so on. And we have two other components. The first one, which is at omega 1, okay, and omega 2, and these two components, which could be very problematic, these two components. Why? Because if omega 1 and omega 2 are close to each other, I mean, for example, one of them is 900 megahertz and the other one is 850 megahertz, so the difference is, I don't know, only 50 megahertz. Then this value is very close to them, and it's not easy to filter out. You cannot filter. It's in band. Could be exactly at the point that you are looking for. I show you one example that in some systems it could be exactly in the middle of your data, and when it is in the middle of your data, you cannot get rid of it. So we have the F1, we have the F2, we have 2F1 minus F2 and 2F2 minus. So you see that these two components, these two intermodulations are very close to our system, to our fundamental signals. I can put a band pass filter here and get rid of all these, but I cannot get rid of these too easily. Okay. So to characterize the intermodulation property of a network, an electronic network, we assume that the V1 and V2 are the same, okay? And then we calculate, we define a value with the name of a relative intermodulation, which is if you put the V1 and V2 the same, so the first one, the value that we have here is alpha 1, V1, and the value that, or alpha 1V, and the value that we have here is 3 divided by 4, alpha 3 VQ. Okay? So the relation between these two, we say that this is the relative intermodulation value for our receiver. What's DBC? DBC? So in the RF electronics, we say dB relative to carrier. We call it DBC because intermodulation relative to my carrier. Okay. Because this is a relative value. Clear? Okay, so we define the third intercept point. This is one, for example, we define 1 dB gain compression point as a parameter of an amplifier. Again, we have another parameter with the name of IP3 or IIP3 or OIP3. And then we say that if the amplitude of each tone rise, the amplitude of the intermodulation rises by VQ. You see that how bad it is. That if we increase the input, then the intermodulation signal could reach to the value of, even could reach to the value of your signal. Okay? As the alpha 3 is small, so when the value, so if I want to show, so this is, you see that the intermodulation has the gain of alpha 3 and the signal has a gain of alpha 1. Okay. So alpha 1 comparing to alpha 3 is very high. But the problem is that this is not alpha 3, this is alpha 3 VQ. So when the V increases, I mean when the input signal, amplitude of the input signal increases, then this is going much, much faster than our signal in the output. Our amplifier gain is alpha 1V, but the third intercept point is alpha 3V cubic.
Relative item is the ratio of
The ratio of the gain of this signal to this signal.
but with that, that's only the first term, right?
The first time, yes. I assume that, okay, these two are not important. Definitely these two are important. Do you know why? Because I told you that this alpha 3 is negative. And I mean, these terms are going to reduce my signal as well. This is another problem. If I guess that, okay, everything is fine with my fundamental signal, I mean fundamental component, which is this component, then we define this. The true one is yes, you define the value by this one, and you know that this is going to reduce my fundamental one. I mean, it's not going to help me. Okay. And then we define the third intercept point as the point that if I increase the input, the fundamental signal and the intermodulation signal reaches to the same level. I mean, the intermodulation signal is so big that could influence my receiving performance, okay? So if you see the slope of this graph and the slope of this graph are different. For example, if my V in is this value, okay, if my V in is here, you see that the fundamental point is very good. And then the third intercept point is much smaller than that. I mean, in the graph, then you see that this is the fundamental, and then this is the intermodulation. But as the input increases, these two gets closer to each other, and I don't like this. What I want is this component to be much higher than this. So what I want that this intercept point be as high as possible. I mean that an amplifier is a good amplifier if its third intercept point is a high value. For example, they said that the third intercept point of this amplifier is 20 dBm, or another amplifier is 50 dBm. So it means that up to 50 dBm of input signal, I can say that my fundamental signal is higher than the intermodulation signal. Okay? So the value for the IIP3, that how we can find, we can measure, we are doing this in, I think, lab 7. So in lab 7 you have a mixer, and then you need to find the compression point and the intercept point of the mixer. It's like this. We know that it follows a kind of, I mean the trend is linear. It follows a line in the log format. So we put an input and then look at the spectrum analyzer. So the input, when I put the input as V1, then I see that the output is, for example, O1. And then I put another input, V2, and then I said that this is O2. At the same time, when I put V1, I see that the output is, for example, I don't know, M1. And then when I put V2, I have M2. I can draw this line, I can draw this line, and then the intersection of these two lines is the intercept point. This is how we can find the intercept point. So we need to do the measurement twice and read the value for the fundamental and the third intercept and the harmonic or the intermodulation twice and then draw the lines. We assume that it's linear, although it's not. We saw that in the P1 dB it's like this. I mean, the gain does not increase linearly at the high. For this, exactly the same phenomena happens. I mean, it's like this. But this is a good estimation. Another shortcut is this formula, that how to find the intercept point. The intercept point is if we have the V in and if we have this delta P. And delta P is the difference between these two at V in. I leave it to you to find out why this formula is correct. If I give a signal, I read the intercept point and the gain, the fundamental one, and the difference between these two is delta P, then I can say that the VIP is delta P divided by 2 plus 20 log of V, only with one measurement, not two measurements. There is no need of drawing the lines, one measurement, and then find the value for the intercept. I leave it to you. It's a kind of geometric problem, so you need to look at these triangles, the angles and the sides, and find this formula. Okay? And I think it's available in your book as well. Question? No? So if no question, I think this lecture finished. We can have a break, and then I'm going to solve the questions, and I think we are a bit behind, but it's fine, because this lecture is very difficult, I think. Lots of new definitions and new concepts. Okay? So we will continue at 4:35. Our system is not timing ready. I mean, if it is timing ready, if this one is not correct, if we put the time shift, the same time shift does not happen in the output, then our system could generate other frequencies. Think about it if you give you one example. Okay. So one of your friends asked that how we can calculate or measure the third intercept point from the graph. I again explain it here. So as I mentioned, if we have Vn into the a nonlinear system like this, then at the V out we have different components of V in, and if it has two components, then for those two that I want to calculate the intercept point based on those is that V out at F1, if I have, which is alpha 1 V in and V out at intermodulation, which is it 3 over 4 or 4 over 3? 3 over 4? 3 over 4 alpha 3 V in Q. Okay. So we have these two components, and then I want to find the value at which the V out of F1 equals to V out of intermodulation. So at one point, I mean, I increase the V in onto the point that these two values are equal. Okay? So this is the definition of the intercept point. If I go to the logarithmic format, I mean, if I look at the V out in dB at F1, it is V in dB plus log alpha 1, and then V out
Shouldn't it be 10 log alpha 1?
actually it's 20 log. because we are doing in power. Okay. At intermodulation, it is again 3 V in at dB plus 20 log of V3. Okay. If you look at these two, the slope of this one, S1 equals to 1. The slope of this one is 3. So this one go faster.
The slope with 3.
This is the slope 3. This is with the slope of 1. So if we draw it here, we say that this is 20 log of V out. This is 20 log of V in. Okay? So this is the slope of 1, and it has a, I don't know, offset. Okay? It's like this. This is the first one, the first line. All right? And the second line again has another offset, but the slope is much faster. It's like this. And then these two are reaching together at one point. And I say that at this point, that these two reaches together, we say that this point is VIIP3, input intercept, third intercept point. And this is VOIP3. In the data sheets, they give you one of these two numbers. Input or output intercept point. Okay? So how I can find these two? Or actually one of them. Because the other one you can find from this equation or from this equation. I give a value, a random value V in. So I have V in 1. I give V in 1. And then I read the V out of the fundamental and read the V out of intermodulation. Where? On a spectrum analyzer. I mean, I generate a signal, I don't know, at 50 megahertz, and I know that two signals, 50 and 45. And I know that the intercept point is at 55 or at 40. Why 55 and 40? So F1 is 50 megahertz, F2 is 45 megahertz. Then 2F1 minus F2 equals to 55 megahertz. 2F2 minus F1 is 40 megahertz. I have the fundamental signal at these two frequencies and the intermodulation signals at these two frequencies.
Which frequency would be given in the data sheet?
No.
Then we have to find it out?
You have an amplifier working from, for example, 2 to 4 gigahertz. And they give you the intercept point graph for all the frequencies. Actually, they measure this in the lab, for example, for 100 points, and then you use a kind of interpolation. Okay? So on the spectrum analyzer, I put the input, and then what a line. So I have two fundamentals and two intercept points. Any of them. I look at, for example, this F1 and this 2F1 minus F2. Okay? I give a single V in value and then read these 2 points, the peak of at this point and peak at this point. So I have two points. which is this point. One of them is this value, one of them is this value. Okay, this is the V out of IN, this is the V out of F fundamental. I change the input value for another number. For example, I go to this point. Again, I read this value and this value. Okay? I have these 2 points. I can draw a line. I have these 2 points. I can draw a line and then find the intersection of these 2 lines and say that, okay, my IP3 value is this point. Is it now clear? We will have one lab on this. I think if you do it by yourself there, maybe.
Usually this intersection point is not there, so we just have to figure out the coordinates and then draw the lines to find
We cannot never reach the intercept point because the main problem is that the intercept point is usually higher than the VCC of the network. I mean, it's more than that. It's a kind of imaginary point. We never reaches that. But it's a kind of parameter that we can compare two devices to say that, okay, this device has a higher intercept point, so it's a better, for example, amplifier. I told you, and I showed here in the graph that this point is usually not there. Here, sorry. Here. So we can measure up to these points. Maybe after this, then it goes like this. It does not go linear anymore, okay? So we imagine these parts.
This is because the VIIP3 is much greater than
the VCC. Usually it's like that. Actually, VOIP3 is more than VCC because the output cannot go beyond the VCC. But VOIP3 is greater than VCC, usually in most of the amplifiers. Okay, questions? So in the final exam, you will receive one question from this lecture. Definitely you will receive one question from this lecture. Okay? Because it's very important concept in the electronics. So in this question, we say that we have amplifier OP77, okay? And then, as I told you, the op amps, in the op amps, the value for the input referred voltage and input referred current noise sources are given. So it's given. I mean, you can simply model these op amp as a noiseless and then put two sources at the input. One voltage source, Vn, and one current, I. Okay? And then it says that we have a signal generator and the output of my signal generator is 25 microvolt. Okay. It has an internal resistance of 1K. It says to find the noise figure of the system and the input SNR and the output SNR. What we have, when we look at this kind of question, what we have, so for the SNR is signal to noise. So for the input SNR, actually, I have the input signal. It's given. So 1 is done. I have to find the noise at the input. What's the noise at the input?
So the VN
Which one?
Cross by noise.
Beautiful.
No, cross by.
Yeah. So this is the input noise. This is the noise which comes from my source. Okay? So I calculate the noise of this resistor 4KT BR and done. So SNR at the input is easy. SNR at the output, I have a signal, I have an amplifier, I amplified the signal. So signal out is the amplified version of the input signal. Clear? Done. SNR in, S in, N in. SNR out, S out, N out. S out is S in multiplied by gain. Okay? N out is the noise that we get from our source, which is N in. Again, multiplied by gain. Plus the input referred gain, I mean the noise of amplifier, multiplied by gain. I put here gain 1, gain 2, because the gains are different. We will see that. Up to here you are agree with me or not? Okay? And then it says that what's the noise figure? And noise figure is easy. The noise figure equals to SNR out divided by, sorry. Actually, F is SNR in divided by SNR out. Okay? And then the noise figure is a dB of this. Clear? And then the noise temperature, I will tell you that it's fine. Okay. So you have one question on this lecture, and I think in lab 3 you are going to calculate the noise figure of an op amp. So the same thing. So the procedure that we are following here, it's the same procedure you have to follow in the lab. So I said about this lecture, not about the op amp. Okay. All right. The source of the noise that we have. If I draw the circuit again, we have plus, minus, and then we had one resistance. So just put. We have the plus minus Vn of the amplifier, and then we have the Rs, and we have Vs, we have In, another resistor which is 1K, and then V out. This is 1 nanofarad. This is 10K. And this RS also equals to 1K. Okay. What are the sources of the noise? So this resistor generate noise. RS. So 1 is RS. So the source of the noise this is R1 and this is R2. Okay. What I can say that the noise that we have is like this. We have Vn of Rs. Okay. What's the gain for that? The gain of different sources of noise are different here. This is what I can tell you because this is op amp. If we have let me just go back to the basic electronic, that if we have an amplifier, okay, what did happen? If we have an amplifier like this, if we have V in if I have a signal at this point, then V out over V in, which is the gain of the amplifier, voltage gain of the amplifier, equals to no, R2 over R1 plus 1. If we have an amplifier and put the input connect the input to the inverter point, then we say that this is AV equals to the gain V out to V in equals to minus R2 over R1. Okay? So the noises which coming from this input, noise sources connected to this input and noise sources which connects to this input see different gains. Okay? This is what I want to emphasize here. That this Vn, this Rs has the gain of R2 over R1 plus 1. This Vn and this Vn has the gain of minus R2 over R1. This Vn, what's the gain for this?
That's only the resistor, so
Okay, the resistor, but it has what's the gain? When the noise moves to the output, what's the gain of that noise? If I model this with the noise-free resistors in series with a voltage source. The gain is 1 because it's already in the output. Okay? So I calculate the value of the noise for this RS and multiply by the gain AV1. I know the value of the VN and multiply by again AV1. I calculate the value for R1 and multiply by AV2. I calculate the value of noise for R2, multiply by 1, and anything else? What did happen to this one? But we model it, okay. You are true that nothing is going to up amp, but we say that if we have this at this point, we didn't assume that okay, nothing is going here. We know that this IN is modeled at the input of the op amp, regardless of what's the input impedance of the op amp. So this IN passes through these resistors and then go and passes through these resistors and make a loop. So this IN, if it wants to go to the output, is IN multiplied by 1K, which is, this is for RS, plus again IN multiplied by 1K. I want to change it to voltage source. Okay, this is a current source. It should change to voltage source and then go to output. This comes from R1. All right. This multiplied by AV1. This multiplied by AV2. So the total Vn of In equals to 1K In AV1 plus AV2. So AV1 here is 11 and AV2 is minus 10. True. We have a 10K divided by 1K. It's 10 plus 1, 11, and in the for the non-inverting, for the inverting it's 10. Clear. I will upload the result for you. You can follow there. But I just want to tell you that each component, how we should look at the components. Okay. So these are the different sources that we need to find and then move to the output and how we can calculate. One more thing is remaining, and that is the bandwidth of this op amp. Because you remember that, for example, for the gain, for the noise of a resistor, the Vn squared equals to 4kTRB. Okay? And this B is the bandwidth of your system. And this B is the effective bandwidth of your system. Okay? I just mentioned at the beginning of this lecture that this is the effective bandwidth. And effective bandwidth, we saw that for a low-pass filter, which we have here, this is a low-pass filter C and R. Effective B of effective is pi over 2 B.
For low pass filters.
Yes, we had in the example. We followed this here. that we have a 1 pi over 2 and then the cutoff frequency of the filter is. Okay. Any other function that you have, then you have to follow through this integral to find the hf squared. So hf is 1 over 1 plus s tau here. If it is 1, I don't know, something else, any type of, for example, second order filter, then you have to calculate this integral to find the effective value. Does it make sense? Clear? Good. And then when they move to the output, as I already mentioned, then we can add the Vn squared of each of them together. Vn squared 1 plus Vn squared 2 plus Vn squared 3. Then this is the output noise that you have. And then put in the formula SNR and find the value. I will upload the result. I think it's very straightforward. So the bandwidth of this system actually, I just mentioned here that the f minus 3 is 1 over 2 pi RC, and R is 10K multiplied by 10K multiplied by 1 nanohenry. This is it. Sorry. Nanofarad, sorry, excuse me. 1 nanofarad. And this is equals to 16 kilohertz. And then the effective f minus 3 equals to pi over 2 multiplied by 16 kilohertz. And this is 25 kilohertz. This is the 3 dB point of the power, and the 3 dB point of the voltage.
The effective bandwidth,
Yeah, this is the effective bandwidth.
3 dB.
Point of the power. This is the F minus 3 dB of the voltage, and this is the minus 3 dB of the power. And then you will receive those results that you saw. Okay. The one thing is the noise temperature. So noise temperature means that if SNR of temperature equals to 10 log of Vs squared divided by 4 KTRB. What does it mean? It means that if I remove all the circuit that I have, this big amplifier and lots of the components that it has, and I just put this, only this one remains, only the RS remains, what should be the temperature of this RS that it generates the same noise that I have now? Okay? When we increase the temperature of a resistor, then it generates more noise. True? Because of this formula. When we increase the temperature, the noise output of the resistor is higher. So I say that if I remove all this circuit and just have this RS, what should be the temperature of the environment, that the noise that I see at the output is exactly the same value? Then we know what is the SNR of the output now. We know what's the Vs, and the R is 1K, and the B is 25 kilohertz, and K is the Boltzmann constant, and then the temperature calculates as 2042 degree. It means that the amount of noise that we have is exactly similar as if we have a 1K resistor and then increase the temperature of the environment to 2042 degrees. Any question on this?
So we are actually supposed to find the temperature.
Yes.
2000.
Yes, we know that the value for SNR. We found the SNR. Now we found it. I mean, after you calculate all this noise, and you know that the S at the output, you know the N at the output, you can find the SNR. So you know the SNR. You know that the resistor of the input resistance of the source is 1K. You know the bandwidths. You should find the temperature.
The output SNR actually.
Yes, exactly. If we put this resistor only and increase the temperature to this value, then value of the SNR that we see at the output is this value. Exactly the same value. I mean, the SNR now at the output is 22.85 dB. Clear? Okay. For the second question, it says that we have a BJT and this is amplifier. So we have a BJT amplifier. We bias the amplifier with 1 milliamp, so IC equals to 1 milliamp. And it says that the beta of the amplifier is also 50. Okay? The effective bandwidth of this system is 100 kilohertz, so B also is given. Okay? We did two tests. First, I put a, and okay, we know that, all right, we did two tests. We put a source and we changed the internal resistance of the source to 50 ohm. And we calculate the noise figure of our system as 3 dB. Then we changed the internal resistance of the source to 500 ohm. And we measured the noise figure as 9 dB. Okay? It says that what is the equivalent for the input referred noise of this system. This is the question. We did two tests. We measured the noise figure. Now I want to model the circuit. Independent of what is the result for this, the question has one hint. If you can change the input impedance of your source and measure the noise figure of any device, any two-port networks twice, then you can model the input voltage and input current source, noise source. Okay? This is what it wants to say. Okay, now I remove this, how I can make it. So in these kind of questions, you should go to the small signal model. Okay? So we need to draw the small signal model and then look at the source of the noise. So if I draw the small signal model, so we have a VS and then RS and then if I have the VNS of the two-port network, this is VN of this resistor, and then another VN which comes from my two-port network, and then the IN, okay, and then the small signal model of the BJT. This is RPi, and here we have a GM VBE, okay, and this is I out, and here is ground. You can have it RO at the output, but no matter. So by the biasing that we have, we know that IC, it says that IC equals to 1 milliampere and beta equals to 50. So based on these two, we can say that GM equals to 38 milli S. What's S? Siemens. Yes, it's not second. Millisiemens. And R pi equals to 1.33 kilo, based on the formulas that you have in lecture 1. GM is, I don't know, IC over VT and go on. And then okay, I have the noise figure, okay? The noise figure, I know that this is the formula, okay? I have the noise figure of 3 dB and 9 dB for two situations. So this is known. This is known. What's NI? From the RS. So this is the NI. Okay. And then this is the, I calculate the NA. Yep. And then I calculate the NA for two situations. So I have two equations and two unknowns. And then find the IN and B.
Of the amplifier.
Sorry?
Noise of the amplifier.
Yes, NA is the noise of the amplifier which goes into the input. Okay? All right. If I want to just write down that the noise of the RS, so the noise of the RS is En equals to 127 picovolt square root of RS square root of B, which is 100 kilohertz. And and this comes from square root of 4kt. Okay, so this is a square root of 4kt. So this noise, if it goes to the output, so I can say based on this small signal model that the I out equals to minus gm r pi divided by r pi plus rs v of n, I write it nrs n rs, your source. So this is the noise which comes from your source. This RS is different in two cases. So in the first one is 50 ohm, in the second one is 500. You know the value for the R pi, you know the value for the GM, and we know the value for the VNRS, 127 picovolt, and then the square root of again RS, which is different for two cases, and we can find the NI at the output. Okay? And then for the other two sources, the first one, which is this Vn, exactly like the VNS. I mean, the gain of this one again is this value. So the I out of Vn equals again to minus Gm R pi divided by R pi plus Rs Vn. Clear? And then the output for this IN, okay? I mean I out of the IN equals to the IN multiply by so this is going to which, I mean, if I want to change this to a voltage, it passes through what? Why?
Come multiply with the parallel between RS and RP.
Passes through RS.
And multiply with Vn.
RS. By RS. Plus RS plus RS.
So we have two resistors here, okay? And these two resistors are in parallel. So the parallel of these two, I mean it is R pi Rs divided by R pi plus Rs. Okay, so this is the voltage. Okay, so this is the voltage that it generates. And then what's the voltage, I mean what is the transconductance of a transistor? It's Gm, which is again multiplied by G. Or it's minus Gm. I mean, if I want to correctly write down, it's like this. Amplitude of minus G. So when a current goes, a voltage goes to the current to the output, it's GMVB. The voltage that you have in the base, how it goes to the output. We have two equations. and two unknowns, and you can simply find that. I mean, in the case 1, you will find A is a number, Vn squared plus Bin squared equals to, A1, B1 equals to C1. And then in the case 2, you will find that A2 Vn squared plus B2 In squared equals to C2. And then you can find In and Vn from these two. Clear? This C is actually, it comes from this formula. It comes from this formula. I mean, you know this value, and then this NA is based on In squared and Vn squared. It's a two unknown equation. Okay, two parameters. Clear? I will upload the result. You can calculate the numerical by yourself. And please do this, because in the exam also you have to calculate these things. So you should be fast in calculations. And you know that the exam time is only 2 hours. So unfortunately, because previously it was 3 hours, but it seems that from 2017 it changed it to 2 hours. So we reduced the number of questions, but you should be fast in calculations.
For the In square and Vn square, should we use the I out for In?
No, I mean, see this I. So when I said that when we have multiple sources of noise, we can say that I out squared is I out of Vn squared plus I out of, In squared.
So basically, In squared is the summation of those two outputs.
True.
Similar for the voltage.
Yes. Similar for the voltage. Okay, if there is no question, I'm going to question 3. So in the question 3, again, the biasing is given. I'm not going through this. I will upload the result. Please go through that because we are, I think, a bit behind. So the only thing that you should consider here, the only part that you should consider here, that we have one RC, and this RC also generates a noise. I mean, if we want to find a input referred noise model of this one, we already know that what is the input referred noise model of a BJT. It is given in your lecture slides. But for this one also, you should make sure that the noise of this is just moving to the base if you want to find the noise, input noise model. So what's the small signal gain of an amplifier? Easy, no calculation. A small signal gain? A small signal gain of amplifier. It's amplifier, it's not one. It amplifies something. AV equals to V out divided by V in equals to minus GM RC. Or if I want to make it more completed, it is RC in parallel with RO, which RO is much higher than RC. And in the input also we have a this is r pi divided by r pi plus rs, but r pi is usually much higher than rs. Okay? So a small signal is easy. Noise figure, I just tell you and you can follow. For this one, how to find the third intercept point. So for the third intercept point, the important thing in the bipolar is this, that IC, the formula for IC equals to IS e to the power VBE divided by VT. Okay? This is the current of a diode. Okay. This is what we have. So and we know that the V out equals to VCC minus RCIC. Okay. So the dependency of the V out and V in, which is VBE, is a kind of exponential. BJT is worse than mass, because in mass it's squared, but in BJT it's exponential. I mean, V out is e to the power V in something, alpha V. In mass, V out is V in squared. Okay, I mean the nonlinearity in bipolar is much worse than the MOSFET. So if I want to model this into the model that I gave you, I mean if I want to model it into the polynomial model that we have for the nonlinear devices, then we need to expand the e to the power x in a series Fourier of this one, okay? 1 plus x squared divided by 2 plus x to the power 3 divided by 6, and so on. And I said that the so on is not important, only the first three. So here we can say that V out equals to minus GM RC V in, the gain of the bipolar transistor, which I just mentioned, okay? And this equals to minus IC over VT RC V in, okay? And then for this IC, I just expand it based on the series Fourier. And I write down it is equals to minus IS RC over VT multiplied by V in divided by VT plus V in divided by VT squared plus 1 over 2 V in divided by VT to the power 3. Is it clear? I multiply this V in, I mean, I move this V in inside the parentheses as well. I move the V in inside the parentheses and then get a factorize of V. Write it down, you will find, okay? So now I can say that what is the value for alpha 1? Alpha 1 is minus IS RC VT squared, and alpha 3, which is this component, so alpha 1 is this component, alpha 3 is this component, equals to minus IS RC divided by 2 VT to the power 4. Okay? And then we had in our lecture slide that V of IIP3 equals to square root of 4 over 3 alpha 1 divided by alpha 3, which equals to VT square root of 8 over 3. Okay, unfortunately I think I cannot start the lecture 3, so it could be fortunately, could be unfortunately, because then the next session I don't need to review anything. We can start fresh. Lecture 3. Lecture 3 is very simple, so maybe next lecture I will combine lecture 3 and lecture 4 based on transmission lines and Smith charts, I mean matching. So we can, any question? No question. Okay. If there is no question, then we can move to a very fast quiz if you don't mind. Okay, could you please log in to the website? Okay, first question actually is, I got some feedback from your demonstrators in the lab, so I was thinking that maybe we have one question to see that, okay, we are in the right track. Okay, so it's a basic question from electrical circuits. I will Someone answered very fast. All right, we have one signal at the input of an amplifier, and the amplifier amplifies the signal, reaches to the level 0 dBm, and we delivers this 0 dBm to a 50 ohm resistor. What's the peak-to-peak voltage over this 50? And the signal is a single tone sine waves. And one more thing is that unfortunately on Wednesday, it seems that at 1 to 2 p.m. the room 110 in building 35 is already booked by someone else. So we cannot have consultation session there. So I will send an email. I will move it to Thursday, 1 to 2 p.m. Because I went there today. It was a mess. You cannot find any place to sit. And please come to the consultation and do study at your private time. This course is not that easy. I mean, this I can say that this is the most difficult course in the engineering, in the whole engineering. Okay? This is what I can say. It's a combination of electronics, electromagnetics, and in advanced level. So maybe the most two difficult topics, and then in advanced level. So it's not as difficult as electrodynamics, but it's not easy as, I don't know, circuit one. Okay, can I close that quiz?
Yes.
All right. If you already answered, then I close the quiz. Okay. So we said that we have an amplifier, and the output of the amplifier is 0 dBm, and here we have a 50 ohm. What is the peak-to-peak voltage at this point? All right? First of all, what is the meaning of 0 dBm? 1 milliwatt. 1 milliwatt, yes, not watt, watt. 1 milliwatt. Okay, so the power that we have is 1 milliwatt. And then the voltage that the power equals to V squared over R. What's this V? RMS. V RMS squared over R. So V RMS equals to a square root of 1 10 to the power minus 3 multiplied by 50 ohm. Can you tell me what's this value? If you have calculator.
224 millivolts.
224 224 millivolt. This is VRMS. And then what's peak to peak?
Times root 2.
No, I'm not sure. Just
Two times
2 times the square root of 2 VRMS, which is 632 millivolt. So it seems that only 7 people are on track. Okay. And it's not very good. All right. The second question. So we said that if we send a single tone signal into a nonlinear system, and then our nonlinearity is exactly the same as what we said before, we have a 1 dB compression point and IIP3 compression point, and we have the formulas for these two. What's the relation between these two? Everybody answered? Okay. Shall I close? All right. But why it's changing then? All right. Okay. Again, we can calculate here. All right. So what we had is V1 dB is V IIP3 divided by V I1 dB equals to square root of 4 divided by 3 multiplied by 0.145. Then, yeah, just can you tell me what's the value for this?
9.195. 9.2.
9. It should not be 9. 4 divided by 3 multiplied by this. It should be 4 point.
817. Yeah, 4.817.
No. Okay. And then 20 log of this because we are going to power. So 20 log of 3.032 equals to 9.6 in dB. And which one is greater? Which one is bigger? I mean, we have two options here. This is option A is correct. Yes. So A is correct. So IIP3 always is like this. IIP3 always is around 10 dB higher than P1 dB. If the system follows this, it's a very rough estimation. If the system follows this kind of nonlinearity, we can, if we have one of them, we can say that the other one is 10 dB higher or lower. Okay? So 11% were on track. All right. And we cannot answer this because we didn't go to the lecture 3, but you can answer if you want. You should know this from basic electromagnetics. So what kind of transmission line can support a TEM mode? What should be the criteria of a transmission line? I mean, regardless of these names. A transmission line can support a TEM mode if and only if it has two conductors. If a transmission line has only one conductor, it cannot support TEM wave propagation. So which of these does not have two conductors? So two-wire line has two conductors. Okay? So it has two-wire line. A strip line also, we will see that it has two conductors. And coaxial cables, definitely you see that it has a conductor at the center and a conductor at the outer. So everybody answered. I just want to close this. All right. Still few are not interested. Okay. All right.